let me start with the reading. You guys largely did the reading. That's awesome. Yes?
I have a question about the quiz on that.
The quiz?
Yeah.
The lab safety quiz?
No, the other one.
There's a quiz, the other quiz that you took other than the lab safety quiz?
Reading quiz.
Those aren't quizzes.
Oh.
The reading quizzes only get administered in class. And they won't necessarily happen with each reading assignment.
So reading questions, are those just for studying, or do they count as a grade?
They do not count as a grade. They are, and as you guys saw, I mean, how were those questions?
Very difficult.
They weren't easy, right? It's not like, here's the definition of displacement. No, they're actually designed to really make you think about what you're reading. And sometimes you'll read it, you'll do the question, you'll get a question wrong, and you'll understand why it's wrong, right? But sometimes you'll go read it, get a question wrong, go reread it, and be like, I don't know what's the deal. Let me ask Khalil. And you should do that. You should come prepared with those questions about the reading, but it's going to be in, I guess, if you're asking me a question about acceleration, hold on to that question till we get there. Because as you'll see today I'm largely going to be developing the earlier concepts. And so with that, we should start by passing out what I classically call how you start a physics class. And how do you start a physics class? Come on, all you guys know this. You start by learning the Greek alphabet. Come on now, it's totally obvious, right? You know, what? That's completely not obvious at all. So, if there's any extras, please hand them back. So what you have on there is the Greek alphabet. And of course, the alphabet that you're familiar with is the Latin alphabet, correct? So what this does, what this sheet is kind of like the corresponding letters. So for instance, the corresponding letter to the letter A is alpha, right? So one of the things you probably notice is that there's a lot of Greek letters that are missing. Why do you think I did that? Well, fairly straightforward reason. If you take a look at the letter I in the Latin alphabet, it corresponds to iota in the Greek alphabet. And guess what the character of iota looks like? I. So there's no need. It's completely redundant. There's no need to include some of these letters. Like omicron is O, and guess what it looks like? An O. So these are the letters we're going to be using, and some of these you're familiar with. Like I'm sure you've all seen a capital delta. I'm sure you've all seen the capital sigma. Some of them you probably haven't seen, like the headphones, which is capital omega. But physics has a problem. You know what the problem is? There's not enough letters in the alphabet to do what we need to do. So, you got to extend it to another alphabet. So that's Greek for you. That's your introduction to Greek. And you should keep that like near the front of your binder. Because I'm going to be writing Greek letters on the board, and you don't want to be the person who says, oh, man, I have no idea what he's doing. It's right there. Just look it up. So, or I have no idea what that letter means. So, now we study physics. What is physics? Well, on some kind of trivial level, you could say physics is the study of the physical world, or the real world. It's the most fundamental of the sciences. And that's true, but it's not really that relevant. So I'm going to give you a definition that's even less relevant. But it's actually true, and it's more specific. And you're all going to do exactly what I think you're going to do. So I'm going to do it. Physics is the study of how vector and scalar quantities transform over space and time. And what should you do with that definition? Certainly not write it down. Why? Because it's a meaningless statement. You don't know what half of these quantities mean. Like, what is a scalar? What is a vector? If I take a 9-volt battery and I press it on my tongue, is that quantity a scalar quantity or a vector quantity that I'm feeling? I don't know. So there's no need to actually go into writing what that is, because it's meaningless right now. But you'll learn what scalars are and you'll learn what vectors are. Right now we're at the beginning. We're at the very, very beginning. And first thing we need to kind of go over is what many of you already know, namely function notation. So for instance, if I write this, how do you interpret that? Is there anyone who's never seen this notation before? Please raise your hand. Okay, so everyone's seen it, which means you're all either taken, I think this was covered in Algebra 2. Is that right? So those of you who took Algebra 2 last year, raise your hand. All right, so what does that notation mean? That's right. It means f is a function of x. So just want to make sure that we all understand that this implies that f is a function of x. And what does that mean? What does that actually mean? Anyone? Come on now. I mean, I'm sure many of you have taken several years. Yes? Ooh, be careful. That's possible. But I'd say, all right, that's fine. We're going to be dealing with only what's called injective functions. So yeah. So you plug in a value of x. What do you get? Value of f. F has a value corresponding to every value of x. So yeah, that's legit. That's a little bit more specific. That's called a one-to-one function. So we know what a function is. So now that we know what a function is, we can actually begin doing what you do. Namely, we need to specify a coordinate system. So, and we need to come to some agreement, at least for right now, what that means. So, in order to specify a coordinate system, you need two things. What are those two things? Think about it. What is a coordinate system? Off the top of your head, just spit it out. It's x, y, right? What do you actually need for that? Let's even deal with a one-dimensional coordinate system, the real number line. What do you need to specify a real number line? You need an origin, and you need to specify a what you call the positive or negative direction. So let's do that. So to do that, let me go tuck this in a little bit. To do that, I'll throw up a number line. This is a one-dimensional number line. All right? And what do I need to specify? Two things. Namely, I need to call which direction positive. First, let me set my origin. Where's my origin? Here's my origin. And I'll call it 0. So what do you want to do now? What do you want to call positive? Which direction? To the right. Does it have to be to the right? Yes or no? You're non-committal, I see. And the answer is no, it doesn't have to be to the right. Well, by extension of the fact that we put it positive to the right, that means negative is to the left. Okay? So let's continue this. Let's make it 2D. In order to make it 2D, what do? Draw a corresponding axis through the origin. Move it over. Yay. All right, that's fine. Make the origin a little thicker. And what do I need to do? I need to do the same thing, yes. Correct. So what do you want to do? Nice. Ooh, he's creative. But we're not there yet. We'll get there. Don't you worry. We'll get there. We will get there. So for right now, I'll make positive going up and negative going down. And so this specifies a whole bunch of things. This specifies your yx plane, right? Here's your y, here's your x. But it also specifies, let's say, where you are geographically on the surface of the Earth. Why? What would this correspond to? North, south, east, west. And for right now, at least for this unit, I want to take this as our kind of common reference frame or a common coordinate system. You'll see we will be manipulating it. Specifically, by the time of Unit 3, we'll be manipulating it. But for right now, I want to maximize your familiarity. So we have a coordinate system. So now that we have a coordinate system, I am going to introduce our first, our first definition. And our first definition is something called position. And what do you think? What character do you think designates position in one dimension? Yes.
Yes.
Correct. It's x. So it's x. In 2 dimensions, it would be x and y. Does it have to strictly be just x and y? No. How else could you specify a point in 2 dimensions? Come on, use your imaginations, guys. Let's suppose I were to take this, grab it, what would categorize that point in 2 dimensions? Or let me even make it a little bit more clear. Hold it, taut. What would specify that point in 2 dimensions? Assuming that my hand is the origin. Yes? But I need something else to specify in 2 dimensions. What you just said is that distance. What does that mean? What? What is that? It's an interesting point, but we'll see. Yes? Well, it's a vector, that's correct. But what other thing do I need to specify this in 2 dimensions? An angle. Right? I have my r, my radii, and I also have my angle. This is next unit's material, though. So I don't want to jump ahead of the train. Maybe not a very good analogy, but anyhow. I don't want to get ahead of myself. In 1 dimension, our position vector is x. And the question is, what's our playing field? In other words, what is the playing field with which space is happening over? Well, in physics, at least for right now, our playing field is time. So in other words, our position function x is happening over time, meaning we express it as a function of time. Function of time. Or in other words, x of t. But I haven't really defined what position is yet. So what do I need in order to define the position? So for instance, let me pick someone. Maris? So, where's your position in the room? That's not what you should be saying. What you should be saying is, Mr. Khalil, that is not a legitimate question. Why is that not a legitimate question? Because you need to ask me with respect to what? And by asking with respect to what am I asking? What am I asking you to define? Beautiful. Correct. So in other words, a position function or the position vector is the point, it's the location of an object with respect to the origin. It is the location of an object with respect to WRT, the origin. Have you ever seen that done before? With respect to? Oh, you got it. So, you're correct. You're saying, okay, I'm going to find the origin of the classroom as being the front, right? And therefore, you're towards the back. So, position is the location of an object with respect to the origin. So now, from your experience, you would think that the most natural place to start a physics class would be what quantity? Distance. Right? I even heard the word distance. Right? I even heard the word distance being spoken. And what's interesting about that is distance is a completely inadequate measure. Completely inadequate. And to understand why, thank you. Right? I'm going to show you why. What distance am I traveling? You can hold it lower. Let's see if we can figure out what distance, how would I actually measure this distance mathematically? How would I define this thing mathematically? I'm not done yet. All right? What distance did I travel? Can someone give me a mathematical definition for it? Yes? Whoa. So you mean my distance is 0? Okay, but I didn't ask that, right? I'm asking about distance. And just so that we actually have this distinction of distance and displacement in our brain. And it's an important distinction because, the most natural thing for us to actually try to do is to explain things from our own intuition. And our intuition tells us distance matters. And it does. But I wouldn't start there. There's a reason why distance is a little bit complex. And in order to understand why, we need to actually look at a different quantity called displacement. So now, since I've told you that distance is not an ideal measure to start with, question is, what symbol should it get? If I were to ask you what symbol I'm going to give to distance, what would you say? Yes? Your intuition tells you what letter? D, right? But I want to reserve my Latin alphabet for the quantities I'm going to be using. So therefore, what letter am I actually going to give it? Be careful. That uppercase delta I'm going to need mathematically. But good guess. It's the lowercase delta. Very good. So, distance. Here's, distance. Let me zoom in 150 and pan that. All right. Distance is going to be given the quantity lowercase delta. And what is the definition of distance? And the answer is, not yet, Mr. Khalil. Not yet. We're going to move on to displacement. Because it's only through displacement that we can actually really start working with what distance actually is. So displacement I'm going to give it a proper Latin letter, D. And the definition of displacement is delta x. And what does delta mean? The change in. And what does that mean? By definition, that means that there must be some final position and some initial position called xf minus xi, where f stands for final and I stands for initial. But each one of these positions are themselves functions of what? Mr. Powers? Very good. So therefore, I can write the displacement as what? X of what? What would xf correspond to? Think about it. F means final, right? So therefore, it would be the final of time. So x of tf minus, that's right. And so at some point, someone in this class is thinking to themselves, wait a second, Cleo. There's already too many letters on the board. All right? Let's see if we can strip this down. Well, for starters, how about instead of calling TI and TF, how about I set an initial time? And what's the most natural thing to set your initial time as? I don't know. Take out a stopwatch. What's the initial time on a stopwatch? That's right. So you can say, and you're always free to do this, you could say let TI equal 0 and let TF be, what do you want to call TF? How about we drop the F? It's called T. And so then the displacement becomes what? The displacement becomes x of t minus x of 0. So all these are equivalent definitions. But one thing I don't like is that it's not clear that if there's a displacement, what must there be? There must also be some type of time. Otherwise, it's a trivial displacement. In other words, there must be some type of spanning of time. So it might be a good idea for me to actually make that explicit, especially when I'm first developing the definition. So I'm going to take this, and before I do this, have you ever seen anybody use this app? It's very cool. This is Microsoft OneNote. So I'm going to move this here, and I'm going to actually write out what displacement is. Displacement is going to happen over what time period? From TI to TF, right? All this is saying is that T spans from what to what? TI to TF. And that's equal to x of TF minus x of TI. And so there we have it. Now we can write it in a more simple way, and we can say, okay, that our displacement, if we call TI 0 and call TF T, our displacement goes from what to what? What time period? It's over what time period? From 0 to T. And so that's nice. That's easy, right? It's very easy to see. Okay. So now that I've shown you the definition of displacement, what do we need to do? It should be completely obvious. We need to do an example. So go into your packets that I gave you yesterday, and there's a packet called Lecture Problems. And I see a lot of people taking notes. And it's quite interesting that people are taking notes. The whole year's notes are basically online already, including this example. So don't feel like you have to. So greater than or equal to between what and what? So you're saying that when I'm writing out d of ti less than or equal to t less than or equal to tf, all that's saying is that t goes from ti to tf. Yes? From yesterday? Share it with somebody for right now. I've got it in the back. You weren't here yesterday, right? Yeah. I recognize you from last year. You're in Scobes' class. So I'm going to write. How'd you get there? How'd you get there? Huh. The nerve. So I'm going to draw this. So this will take me a second, unfortunately. It doesn't copy over for some odd reason into this. 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you go -1, -2, -3, ... We don't really care about the negative side because all of our positions for this example are where? On the right side of the axis. Right? So notice at time equals 0, x of 0 equals to what? You can just read it off on x of 0 is 0, x of 1 is 2, x of 2 is 7, x of 3 is 1. So notice, is the time axis drawn on this line, yes or no? No, it's not. This is a very simplified kind of graph. And so our points are here, 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 and here. Okay? Everything's drawn out. And so what I want to do is I want to actually work out the properties of this displacement and also to calculate distances. So let's start. I'm going to pan this up. Pan this up. Okay, so now I want to find the displacement from time equals 0 to 1. All right, so displacement from t going from 0 to 1. Right? And what is that equal to? It's equal to x of 1 minus, you just spit it out, x of 0. And that's equal to 2 minus, and that's equal to 2. And so what is the distance that it travels? Let me see. How am I going to do this? I need to zoom in a little bit. So now I'm going to draw a line here. And so the distance it travels from 0 to 1 is equal to what? How much? It's obvious. You start at 0, you go to 2. What distance did you travel? 2. Nothing hard. And of course, I'll give it units. These are meters. This is meters, 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 meters. I'm not a stickler when it comes to units. or significant figures. We do real things here. We do serious things. So anyhow, so there's the displacement, there's the distance. So now let's go and do the displacement from 1 to 2. What does that equal to? Spit it out. Ready, go. x2 minus x1, which is 7 minus 2, which is 5. The distance it travels in that time period is how much? 5. Right? And then you have the displacement from t equals 2 to t equals 3, which is x3 minus x2, which is 1 minus 7, which is negative 6. Negative 6. Let me actually give this some space. What distance does it travel? Correct. The distance it travels is 6 meters. What's the total displacement? In other words, what I'm really asking is, what is the displacement from what to what? 0 to 3. So what do I do? Well, I'm going to need more room. That's the actual answer. Khalil, you need more room. Because if you take a look, let's add each of the individual displacements algebraically. So what does that mean to add it algebraically? That means that it's equal to x of 3 minus x of 2 plus x of 2 minus x of 1 plus x of 1 minus x of 0. And what is that equal to? Algebraically, what's it equal? Notice what happens to the x of 2's? What happens to the x of 1's? And what are you left with? X of 3 minus x of 0. This is a mathematical property called a telescoping sum. A telescoping sum. All of your deltas are telescoping sums. And it's that property of it being a telescoping sum that allows you to do many of the nice things in calculus. You'll see later when you get into calc, especially when you get into integration in calculus, that it's this property that is essential. So it is a very important property, and it's one that cannot be overstated. So now what does that equal? What does x of 3 minus x of 0 equal to? What's x of 3? 1. What's x of 0? 0. And notice we could have arrived at this by doing what? Adding each of these individual displacements. 2 plus 5 is 7, plus negative 6 is 1. What's the distance traveled? What distance was traveled? Oh, be careful. Is it the absolute value of all of them, or is it? Well, first let's compute it. What is the computed distance traveled? 13. So the distance traveled from 0 to 3 is 13. Now, let's actually go into trying to formulate a mathematical definition. Even though this is futile. We're formulating a mathematical definition for a quantity that we're not going to be analyzing largely in this class. But it's important that you understand why it stinks. So, you said it. Distance is going to be what? All the previous displacements combined? Okay, but then here's a question. Is that absolute value of all the individual distances needed? Why? Because they're already positive, right? So what you're pointing out is something important, though. That the distance between any 2 points is going to be the absolute value of the displacement between these 2 points, assuming that you didn't do what? Beautiful. Beautiful. Repeat that louder. Assuming that you didn't turn around. In other words, if you want to compute distance, you have to account for every change in direction. What that looks like is something pretty nasty. What that looks like is you have to split up an interval into a series of points, right? So x0, x1, x2, x3, not plus. So here's your series of points, x4, right? And then your total distance is going to be what? Absolute value of x1 minus x0 plus the absolute value of x2 minus x1 plus the absolute value of x3 minus x2, and so on and so forth. And notice what doesn't happen here. You don't have that property of it being telescoping. In other words, you can't strip out that minus from the absolute value. Distance is terrible. We're talking about displacement. Any questions? So now that we have some notion of what each of these things are, we move on to the next subject. Right? We now know what distance is. We know what displacement is. Now we can talk about speed and velocity. So, now speed, you guys, I mean, come on now. I can't make believe that you know nothing. You have knowledge. What is speed? That's right. In other words, and what speed am I talking about? Yes. Very good. Average speed is defined as, which in what I'll give it a letter. The letter I'll give for average speed, I think it will be S. Doesn't really deserve an S, but I'll give it one anyway. S is defined as the distance divided by the change in time. And this is the definition of average speed. So if I'm going to denote an average, I need to give it a bar on top. That bar means average. Average speed and average velocity, by definition, occur over a period of time. You cannot talk about the average speed in an instant. It's called an instantaneous speed. Similarly, you can't talk about an average speed over an instant. That's called instantaneous. You can't talk about an average velocity over an instant. That's called instantaneous velocity. Average velocity, by definition, occurs over some time interval. And similarly, what do you think the average velocity, definition of average velocity is? Yes? Anyone? Yes. Correct. There is the displacement over the change in time. But remember, what's displacement? The change in. I see you're about to say it. Displacement is the change in position. That's right. So I can rewrite this as delta x over delta t. And anyone with any mathematical background, I would close the computer. Even though you're probably taking notes, We can talk about it later. But anyone with any mathematical background, when you see average velocity being equal to delta x over delta t, what should that look like to you? That should look like a slope. Do you see a slope? Yes or no? What is slope? Someone give me a definition of slope. Anyone? Yes. Rise over run. Well, what is your rise? The change in what quantity? Change in y values, right? What's your run? Change in x values. So I'm just kind of going to put this in your head for right now and get back to it in a little bit. Right now I want to kind of deal with average speed versus average velocity. And what I'm going to elaborate on very shortly is that average speed and average velocity, both of them, are not equal to the arithmetic means of a sequence of speeds or velocities. So in other words, if you have a set of speeds, let's say between here, where do you want to drive to? Come on, we got to drive somewhere this weekend. Anyone going anywhere? Point Pleasant. Okay? So between here and Point Pleasant, you need to take, I don't know, 287, Garden State Parkway, and what is that, 35 at some point, maybe 37? Okay, so here are your three roads. Your average speed on 287, say there's traffic, is 30 miles per hour. Your average speed on the Garden State Parkway is 60 miles per hour. And your average speed on 37 is 15. How would you compute the average speed of the entire trip? Anyone? Talk to each other. Write them down. Talk to each other. Come back to me in a minute. Nice. Mr. Khalil. Ditto. Oh, I'm sure. I haven't talked to him since he left, but yeah, I'll probably be in touch with him in the next couple months. I'm sure he's doing great. All right, so any answers? Yes.
Since the average speed is the displacement over the, so we're finding the average speed, I guess. So do we just add the average speed of each road that you travel and then divide it by the number of average speeds that you added?
Ooh, okay. And the answer is no. But that's exactly what I wanted to flesh out with the question. In other words, you couldn't do that problem based on the information I gave you. And what I wanted to show you is that the average speed is not the arithmetic mean. You can't just take a sequence of speeds, right? Sum them up and divide by the number of speeds and say that's the average speed. The average speed is the total distance divided by the total time. But it's very good that you said that, because it's exactly what I'm trying to. I want to make sure that we get rid of a lot of the things that we do. So anyhow, with that, I want you to go to your next lecture problem. And anybody want to read it? Someone read it out loud. Go ahead. It's right there. Just read it. I don't have it in front of me. I'd read it myself. Bowers, come on.
All right.
Whoa, 1 second. All right. Go ahead.
Speeds up to 200 kilometers per hour for the next 4 hours.
Uh-huh.
And then slows down to 120 kilometers per hour for the next 6 hours.
Okay. What's the average speed? Yes. All right. So now, the quickest and dirtiest way to do this is create a table. These are straight-up table problems. And trust me, if you didn't create the table, it would be twice as much work. You just throw up the table, bang, bang away. So what do we have here? It goes 180 miles per hour, right, for 2 hours?
Yeah.
All right. Then what happens?
Speeds up to 200 kilometers per hour for the next 4 hours.
Right? And then what?
And then slows down to 120 kilometers per hour.
Beautiful. So what is this begging us to do? Compute all of the distances. So this is just a straightforward algebraic rearrangement. S bar is equal to delta, right? Or we're changing time. So therefore, your delta is equal to S bar times delta t. So you just multiply them. You got 360 here. You got 800 here. And you got 720 here. And in total, that's some number. What is it? 1880. In how many hours? In 12 hours. And what's that average? And the answer is, the average speed is 1880 over 12. We're done the problem. You can plug it into your hamburger helper if you please, but I don't care. What I generally am looking for is algebraic beauty. So there's your average speed. How much is that approximately? Looking at that roughly, it's going to be less than 200. 157. It's not a chemistry class. So it's 157 mph, which is a terrible set of units anyway. Any questions? So now I want to go into the next example and kind of flesh out the differences between displacement, distance, average velocity, and average speed. So that next example, I think there's 1 billion steps. Is that right? So great. Got 1 billion steps ahead of us. Fantastic. Let's actually go through it. So let me zoom in. All right. How's that look? Can everybody see that? Great. So balloon drifts towards the west in 150 meters towards the west in 50 seconds. Wind suddenly changes and the balloon flies 100 meters towards the east in the next 25 seconds. Okay? What is this begging us to do? Right off the bat. It's begging us to establish a coordinate system. Right off the bat, you draw it. Physics is one of the few classes, other than art, where you actually get credit for drawing something. So I'm going to write this up here on the board. Go back to good old chalk. So we draw our coordinate system. And which way do you want to call east? To the right. West is to the left. So what does this do? It goes 150 meters to the west, right? Which means that it starts at, is that a displacement or a position that it's giving you? Someone said it. It's giving you a displacement. Technically, you could say it's giving you a position as well to some degree, because it's implicit that the origin is at 0. But that's actually a displacement that it's giving you. So it's going 150 meters, right? So now what position is this person at that time? If we take the left to be negative. It's at negative 150. Okay? And then, what does it do? It travels 100 meters towards the east. Right? Then it goes 100 meters towards the east. What's its final position? Right off the top of your head. Its final position is going to be negative 50. So let's actually work this through. So let's just write these up. What distance did it travel in the first 50 seconds? So A, it travels, how much? 150 meters. B, 100 meters. And C, 250. What's its displacement? So this is D, E, and F. Its displacement in the first 50 seconds is negative 150. Its displacement in the next 25 seconds is, what is it? During the next 25 seconds. Positive 100. And the total displacement is negative 50. And then we go to the velocities and speeds. GHI, and was it JKL? So what is going to be the speed over the first 50 seconds? It's going to be 150 divided by 50 seconds, right? Which is 3 meters per second. And then over the next 25 seconds, it's going to be, so you have 100 divided by 25, which is 4 meters per second. And what is the average speed? It's going to be 250 divided by, what's the total time? 75. What does that equal to? So 3.33. Notice yet again that the average speed did not equal the arithmetic means. Similarly, with the velocities, what do we get? Negative 150 divided by 50 is negative 3. Can you guys see that, or should I just go to the other side? And it's pretty trivial. I mean, this problem is very trivial, but just want to make sure you guys have the J, K, L. So you have negative 150 divided by 50. The next one would be positive 100 divided by 25. And it's negative 50 divided by 75. Right? This is negative 3. This is positive 4. This is negative 2/3. Or negative, I don't know, 0.67. So a number of things to look at. Notice, did our average velocity and average speed equal each other at all? No, not at all. Any questions right now? All right. Let's see, where are we at? We're done that. We're done that. Moving at a nice clip, guys. Now it's time to go to Pear Deck. So, we'll hop in Pear Deck, and now I actually get to see what you know. Sure. Or you can share with somebody. It doesn't really matter. Because anyhow, I want you guys to talk with each other as you're answering these questions. I don't want you to suffer in silence, no matter how much you want to suffer yourselves. All right, is everybody invited? Or is everybody getting it? How much time do we have? 15 minutes? Nice. All right, session dashboard. So, waiting on Casey, Gina, Henry. Actually, this gives me an opportunity to take attendance, too. Is anybody missing? Who? Cool. Margaret, Maris. No, it's peardeck.com/join. Thomas's. No problem. All right, so I'm going to start this. Here is the start. Walking the dog. You and your dog go out for a walk to the park. On the way, your dog takes side trips to chase squirrels or examine fire hydrants. When you arrive at the park, do you and your dog have the same displacement? Yes or no? You can discuss it amongst yourselves. All right. I forgot to break out my hourglass. Five seconds. So it looks like you all got it right. Very good. Yes, you and your dog have the same displacement. Did you travel the same distance? Obviously not. Does displacement of an object depend on the specific location of the origin of the coordinate system? I'll give you some time for this. I'll give you a minute. Don't be afraid to get your hands dirty, guys. "15 seconds. Five, 4, 3, 2, lock it. What's the answer? Anyone want to volunteer? Yes.
No.
Why?
Because it doesn't matter where you start from, as long as you end up the same distance away from the...
Yeah, but what this is asking is, does it depend on the location of the origin? In other words, if I put the origin at negative 50 meters, would the displacement that I go matter?
Well, are you starting like from this, like no matter where the origin is, like you'll be starting from there, right?
I'm starting from the same position in space, correct?
Wait, okay. So if you originally were starting at like 100, but like, okay, yeah, I think the answer is no because like as long as it's like the same distance, it doesn't matter where the origin is.
Very good. So what this really means, very, very good. What this really means is this. I'm going to actually imagine that we're all on the same plane, right? So imagine we're all on the same line. Don't even take this plane or this line into account, just this line. Okay? Relative to you, I'm one desk ahead. Now, if I go some displacement, one desk, right? What is my displacement relative to you? My displacement, not my position. My displacement is, I went from 1 to 2. So my displacement's 2 minus 1, which is 1. Now your name is? Brian. Relative to Brian, my position is 1. What my displacement was? 1. I went from 0 to 1. So it doesn't depend on whether I place the origin at Brian or I place the origin at, what's your name? Emily. So it's independent of where I place that origin. Notice what vector did depend on the origin. Clearly, the position vector. Relative to Emily, I was 2 away in terms of my position. Relative to Brian, I was 1 away. But displacement is independent of the origin. If the position of a car is 0, does the speed have to be 0? "30 seconds. Five seconds. 3, 2, time. Okay. Anyone want to volunteer an answer? Come on now. Don't make me roll dice. Don't make me roll the dice. Yes.
Well, I said no, because it's hard to be passing through 0 at
Correct. Let's say walking and Gabby. If I put the origin at Gabby, right? What's my position at that point? It's 0. But I clearly have a non-zero speed. So does the odometer in a car measure the distance or the displacement? "15 seconds. I love it. 5, 4, 3, 2, time. The answer is? Distance is correct. And just to verify that it is the distance, consider this. If it was displacement, who drives here? If it was displacement, if you had a reading on your odometer when you left home, what would that reading be when you got back home? 0 is correct. So have you ever observed that? Would you ever buy a car that does that? No. You would never buy a car that does that. Why? Because you had no idea how many miles are on the car. So how would you measure displacement? As a side. What instrument in many new cars actually could measure displacement? Yes. GPS is correct. What on Google Maps would measure displacement? Yes. How? Anyone? I don't know if Google Maps has this capability. Yes. Meaning in the air. Correct. That would measure your displacement. Although technically even the air would not measure your displacement. Why? Because you're constrained to move on the surface of a curved object, namely that of the Earth. Right? So even if you're traveling there by air, you're traveling over a curved surface. The displacement from here to China would be a line that passes through the center of the Earth. So the speedometer of your car, what does it measure? Velocity or speed? No need to formally answer it. Give me an informal answer. Anyone want to spout it out? Yes. Correct. In the very nature that the odometer is measuring your the very fact that the odometer is measuring distance tells you that the speedometer must be measuring speed as well. But yeah, I mean, you're one way to definitely determine that your speedometer is measuring speed is what? What would you do? You would go on a racetrack, right? You go on a racetrack, you take your Ferrari or your Honda Fit, one or the other, right? And what do? You drive in a circle, right? And by driving in a circle, you complete one lap. And if your speedometer measured your average velocity, what would it measure? 0 is correct, because your displacement is 0. So therefore, your speedometer must measure speed. And this is the type of thought processes that you're going to start doing when you start learning how to think physics. And you'll see there's a whole thought process associated with this course. So, how much time do we have? 2 minutes. Fantastic. So let's actually do these problems. So you drive 30 minutes at 30 miles per hour, then for another 30 minutes at 50 miles per hour. What was your average speed for the whole trip? 30 seconds. Should be totally obvious. Anyone? Anyone? Why? Why can you look at that and say 40?
Spend half your time going 30, half your time going 50.
Correct. In other words, here you can take the arithmetic mean, and the reason is because the average speed is actually a weighted average. And so if your weightings are equal, guess what? Then you can take the arithmetic mean. But for the most part, they're not. So for instance, the next question, they're not. So I recommend you chart this out. What nerve? Class is not over yet. Man, you guys are a tough crowd. As you know, no homework for the weekend. We shouldn't even be here yet. And, oh, did everyone do their Flynn safety contract? This would be a good time to collect it. You can just hand it up, or, you know what? I'm going to place them right up here. Just drop them off right here on your way out. Have a great few days off. I will see you on Wednesday. No? I'll see you on Tuesday. All right. You guys are going to be ahead of the other classes by quite a bit. Right over there. Later. Have a great weekend, guys.